Hey, welcome back. Let's talk sheet metal milling. I have some parts that I have one part that I need to make from beryllium copper. First of all, because otherwise the comments will be flooded with beryllium copper comments, beryllium is toxic. Beryllium copper can be toxic too. So take your precautions when you work with materials like this. Read the material data sheet, understand it, and take some precautions. Don't grind, for example, on beryllium parts. If you can, skip it. If you have to grind it, collect the dust with a appropriate dust extractor, wear a respirator, wear gloves so you don't get the beryllium copper or beryllium dust on your skin and transferred into your food and then into your body and then you die. Don't do that. Also keep a healthy distance between your coffee and your beryllium copper. Center to center distance should be at least 500 millimeters. Okay, that out of the way, we have a piece of 0.5 millimeter thick beryllium copper and we need to mill a part out of it. Not only contour tracing, but also some pocketing. That's a little bit tricky because you need 0.5 millimeter is not very thick and the sheet doesn't come very flat either. So that's the first problem here. And doing 8 years of prototyping at work, we had to do that very often. And while vacuum work holding is viable and certainly works for this part, I was never a big fan of it because you have the constant power draw of the vacuum pump, you have the investment in a good vacuum pump, you need a good vacuum table, and so on and so on. It's a whole thing if you want to go into vacuum work holding. I have a vacuum plate, but it's not suitable for this task. It has very wide grit and doesn't keep thin stock as flat as it would need to. That said, what I prefer to do is I take a piece of aluminum tooling plate. This is cast aluminum plate that gets surfaced with a huge face mill. You can see the mill marks here. Maybe on this piece a little bit better. Those lines that go across the stock, those are the end mill feed marks. So then the face mill has probably 2 to 3 meters in diameter to create the stock. These are dedicated machines that are just here to surface this tooling plate. So you buy a piece of this tooling plate, it's not crazy expensive and it's worth it. You clean it, you stone it very, very carefully so you don't get any raised areas. For example, I had a small ding here where material was raised because somebody put a big old dent in the material. Just stone it flat. Clean it with steel wool and acetone or a piece of Scotch-Brite and acetone. Gloves, of course, so you don't get your grubby skin grease back on the part. And you do the same for the sheet metal. You cut it in a way so you don't make it out of flat like crazy. Ideally would be to saw it. In this case I sheared it. And what I also did, I created a hinge out of, this is Kapton tape. And I created a hinge, I glued it to the top and to the back of the plate so I can apply my super glue. Then I can just fold it over, flatten it out, put another piece of aluminum tooling plate on top of it, a spreader bar, then 2 or 3 C-clamps. I have to check if my C-clamps open up wide enough for the spreader bar, but I think they will. And that's the whole process of gluing it down, and then we'll leave it for a day. You really need to leave it. You cannot just slap it on, clamp it, wait 10 minutes and go on. At work, when I was in a hurry, sometimes 1 hour was enough. But when you milled out parts and you smelled at it, you could smell that the super glue wasn't cured already. Super glue under this circumstances is relatively slow. And you could use activator on one side, but I didn't have very good results with it, so I don't do it. So I cleaned the beryllium copper sheet up here already with a piece of Scotch-Brite that had a little bit of WD-40 on it so I don't create airborne dust. Then I cleaned it very, very thoroughly with a piece of kitchen tissue and acetone, and I just will go over it again, wipe both of it down, so we're absolutely on the safe side. Now for the super glue. Well, you can use everything. Super glue is not a crazy specialized thing. I use super cheap and super expensive super glues. I use the rubber reinforced black Loctite 380 Black Max. It kind of everything works. I use this Mate 85 made by Henkel. I buy this because I'm used to it. This is the stuff I used at work for this exact task, and it always worked. So that's what I buy. It's a very thin super glue that spreads out very nicely and holds very well. So we're going to apply the super glue, fold it over, do our whole story with the plate and spread bar and the C-clamps. And hopefully we don't create a huge, usually it's a huge mess when you do this, but that's also why I have a little bit of foil here, so I don't super glue my bench. Also, I will add a second layer of foil between the sheet metal and the top plate, so I don't glue the top plate to the sheet metal. This would be rather annoying. I tried it, it's really annoying. So I think that's enough talking for now. Let's do some super gluing. The super gluing needs to go relatively fast. Once you start to apply it, there is no way back. And also note that I'm using a flat plate without any slots or grooves cut into it. There is a different way of using super glue work holding, and that is to use a plate and cut a nice grid pattern into it. This allows the super glue to go out of the way and work seat onto the aluminum or whatever material you use for a sub plate, and that works excellent. But usually when I do just prototyping, it's too much work for my taste. I just take a flat piece of aluminum, and when I press down the sheet, my stock onto the plate, it usually is flat enough for 99.9% of the work I do. So let's super glue. Before we super glue, let's take one final swipe with the acetone, just in case some dust dropped on here. I did the same work with gold sheet. I milled parts from 0.2mm gold sheet metal that has been rolled to that thickness, and we did exactly the same procedure. I say we, I did. I came up with the procedure for the gold parts, and the engineer I worked with perfected it, and then we proceeded on to make hundreds of parts out of gold using this technique. Gold, by the way, is terrible to work with. It's insanely ductile. It tends to gall up cutters like crazy. It chip welds, it's soft, it's the metallized nightmare of machinists. Okay, a nice even spread. Now we flip over the sheet metal. And usually we will have a ton of squeeze out now. And this is the beauty of the Kapton tape hinge. We don't have any alignment issues. So now we add the foil and the top plate and the spreader plate. And we slide everything to the front of the table so we can center out the C-clamp, and then we clamp the crap out of it. This needs to be relatively quick. We could add a fourth one. If I had my hydraulic press in place, I could also just put it in the press for clamping. Then with the spreader bar vertical, so it has a higher stiffness. So we tighten this to a decent squeeze. Then while we're here, super glue. Wipe down the darn nozzle of the super glue once you're done. This prevents you from creating a crusted up nozzle on the super glue, and we hate that. Okay, there we go. Let's let it cure for a few hours, and then we go to the mill and cut her apart. Several hours have passed, and I think I can undo the clamps. So let's see what sticks together and what doesn't. This plate should come right off. The foil comes right off. And this lower piece comes off too. And we have one nice piece of very flat glued down beryllium copper sheet. We can peel off the Kapton tape here. More or less. More less than more. Well, can stay on too. Okay. We also can take a chisel and remove the super glue from the sides of the plate. That's kind of important for work holding them on the milling machine. Doesn't help if there are huge gunks of super glue on the side of your plate when you try to hold it down flat. I'm a little bit careful. I don't want to cut myself here on the edge of the sheet metal. So that's the reason why I'm using a knife towards my body, of course. There we go. That cleaned up nicely. Now we need to get rid of all these super glue chunks on my bench. So we're still on the back side of the plate. Just to make sure there are no raised areas. Doing a quick sanity check with a 2-micron indicator just in case there's something weird happening. In the center line we have pretty much 0. Here on the end drops off rapidly. The sheet metal is overhanging over the aluminum plate a little bit. So in overall, I'm not sure how consistent the thickness of this beryllium copper sheet is either, but this will do fine. We are over at the CNC milling machine, and as you can see there is only one on here. Usually I have two, but I stole one to put it on the Deckel FP1 for time being. To hold the subplate with the sheet metal glued to it, we need to reverse the jaws to get a larger range on this vise. And on these Garant extra vices, jaw change is very easy. You just pull them off. They are held with two leaf springs back here and are pulled in against this dovetail shape. So after you clean the vices, you can put these jaws back on, just flipped over. Okay, these are jaws with some grippers. They have spikes that bite into the material, and these will hold this rough sawn plate. This is just cut with a circular saw. These jaws will hold the material absolutely safe with a deft grip. To pull this out of the vise, you probably would lift the machine off the floor. Here I'm at the about center where we're going to mill, and we call this 0. Let's move around a little bit. So this is about -2, so minus 0.02 millimeters, also known as 20 microns, or 2/100th of a millimeter. It's a little bit hard to translate that into English because we always say hundredths for 0.01, also known as 10 microns. So usually, let's talk microns here. So this is minus 20 microns. This is the other side. This is plus 20. Let's go, the part is 60 millimeter wide, so let's go here. This is plus 40. This is plus 10. Let's go in Y. Okay, this is minus 30. And over here we get 0. I have a part. This is what the contour is looking like. This contour you see here is about 0.2 millimeters lowered into the part, so it's a pocket. And when we look at this, this will be fine. Well, it's 70 microns corner to corner, but this pocket here is just to give a vacuum chuck something to attack this piece here and pull it down onto a ground plate. So it's basically an inversed vacuum chuck, as far as I understood. We're now touching the thickness of the material here. A touch of C height in the center of this plate. I have a 1 millimeter end mill in here already. 1 millimeter 3-flute carbide. And my preferred way of touching off on a CNC without a Renishaw probe is a piece of round carbide. I drop the cutter below the diameter of the pin, like this, so the piece of carbide does not pass through under the end mill. Then I just slowly raise the C-axis until the pin passes through under the end mill. Then I'm exactly the diameter of the pin, which is 6 millimeter in this case because it's a broken end mill, away from my sheet metal surface. My origin on the part is in the right left corner, so I'm just finding. So I'm just eyeballing the piece into place. So this is Y0 and X0, and we're good to go. That was easy. Okay, here's a quick glance into CAD, and I have a 3D model of the part with the structure on the back side and chamfers on the front side. And here you can see the bend that we need to put in the final part. But for now we want to look at the cam part, because that's what we're going to do first. And the way I machined this is, first I did a pocket operation. This is a 3D pocket operation, and I'm running a 1 millimeter flat end mill at 20,000 RPM with a feed of 1,500 millimeters per minute and a depth of cut of 0.05 millimeters to rough out most of the stock, and I leave an allowance of 0.025 millimeters on the sides and on the floor. I followed up by just cleaning up the floor of this pocket. This is just cleaning up the floor, and it stays clear of the walls by 0.2 millimeters. I don't want to finish wall and floor at the same time. That's a good general rule. So I stay 0.2 millimeters away from the walls just to be safe. And I'm using the same speeds and feeds here. Then I come back with a contour toolpath. With a step down of 50 micron, 0.05 millimeters. And the same speeds and feeds again to clean up the walls. Always with a nice small lead-in radius so we don't get a mark from the end mill there. And this cleans up the walls. And then finally we cut it out with a 2D profile. And as you can see back here, I'm cutting it larger than the tab. I have a second model here with the tab unfolded and elongated to give me some stock to work with for bending. And the 2D contour is programmed, same speeds and feeds, 1,500 millimeters per minute, 20,000 RPM, but I'm running a 2-degree ramp. So I'm continuously ramping down on the contour until we're through the stock all the way. And as you can see, we're cutting through the material quite a bit here, just to be sure that we clear the corner chamfer of the end mill. This strategy with ramping down with a very fine feed and with no stock to leave usually leaves parts that are perfectly on size within a few microns, or a few 10 microns in case of CNC router, but works excellent. This works in soft materials like this beryllium copper. This works in stainless steel. It works in hardened spring steel. It's always a surefire way of cutting out parts from sheet stock. Works way better than plunging through the material and trying to take a 0.5 millimeter cut with a 1 millimeter end mill in one go. This usually leaves a terrible finish. Tool gets hot, burns up, and things like that. Just terrible. So ramping around the part takes a little bit longer, but is 100% fill proof. So let's run a simulation here. Cutting the pocket, floor finish, wall finish, and the final cutout of the part. Part is milled completely. As you can see, I milled through the copper sheet into the aluminum subplate. You always do this when you cut thin materials on a sacrificial plate, because the end mill might have a corner chamfer, and if you don't cut all the way through, you end up either with the stupid onion skin that you have to remove, it means a very thin layer of material, or a burr from the chamfer on the end mill. That's dumb too. So just cut into the sacrificial plate. That's why it's called sacrificial, and get a perfect clean edge on the part. Now we clean off this mess, try to get rid of most of the chips, wash it off with some acetone and have a look at it. Not acetone, it's propane alcohol. Let's see. No compressed air cleaning this one. Just washing it down with the, that's propane alcohol. Yeah, it's flammable. I'm not no smoker. How do we get the sheet metal off the sacrificial plate? And the answer is acetone. Well, there are many different ways. You can get a razor blade iron on the side and pry the sheet metal off, or you just drop it in some acetone and wait. And at least the larger piece here already released, and this will take some more time. But this is the lowest impact way of releasing these parts. You can also throw them in the ultrasonic cleaner in a heated bath. This will also kill the superglue. You can mechanically release it by prying with a razor blade, or you can use acetone. Sometimes you can beat the back side of the sacrificial plate with a rubber mallet, holding it in the hand, and the part will fracture off. Now, still have to deal with superglue residue. But for sensible parts, superglue removal, acetone works the best. And yeah, plastic kitchenware is resistant to acetone. As you can see, I released it from the superglue. Took some time, wiped it down with acetone. It's a clean part now, safe to handle. Solid beryllium copper is not really a problem, only dust and very fine chips that you inhale. This is the sample part. As you can see, we have this lash up here. It's broken off on this part. This will need 2 bends to be put in it. That's probably the last step. But another feature that we need to add is this chamfer all around the part. This is a 5-degree chamfer to half the thickness of the material. And I was a little bit curious of how to do it, but the answer is pretty simple. I can just mill it with a 5-degree tilted part with the side of an end mill going climb cut. I demonstrated this technique in a very old video of mine. It's called thinning down sheet metal, and it's basically the same, except for back then I used it to make sheet metal thinner without supergluing it down, and this time we're using it to cut a chamfer. So let's go to the milling machine and have a look. Okay, we're over at the FP1 milling machine, and we're about to cut those long 5-degree chamfers on the sides of the sheet metal. And the way I'm going to do is I tilted the vise 5 degrees towards the machine. I have the vise on the indexing head, and the indexing head is tiltable and rotatable. So tilted it 5 degrees this way. This will give me already my angle. I have the sheet metal vertical up against a large ground block with the upper edge here flush with the block. I ensured the flushness with a magnet on both sides and pushing the sheet metal up against the magnets, then removing the magnets after clamping the piece in the vise. The sheet metal up here is loose. It doesn't need any work holding up here. The end mill, when you go clamp cutting this way, will push the sheet metal up against the block, and this ensures a half decent even chamfer. I'm using a 6 flute 6mm carbide end mill, finishing end mill, and we're running at 2000 RPM and a feed of 500 millimeters per minute. And I'm going to take 2 passes of 0.125 millimeters. I blued up the piece of the sheet metal here, and this will help me to touch off the end mill. Then I will feed out, move in the Y direction to take my depth of cut, and then I will engage the power feed. I proceeded on to mill the chamfers on the short sides of the sheet piece, and for that I had to change my orientation of the large block here to vertical, and I added also a tooling plate to move the pressure of the vise up a little bit further towards the part. Otherwise it gets a little bit shaky. Milling the chamfers on a manual mill went very well. When you look at this piece, you can see that those edge chamfers look half decent even, considering this is 0.5mm sheet metal. I didn't go, after talking to a customer, he told me that these flags here break off in this area because they used to run this chamfer all the way around. And that thins the material down to 0.25 millimeters, and that creates an area where the part will break. So we're leaving it out, and hopefully they hold up better that way. What we need to do now is, this flag that sticks out here needs a C-shape bend into it, and I want to try something new for this, because trying something new on a customer part is always very exciting. We want to try rubber pad bending or rubber pad forming. That's an industrial process, but I'm hacking together my own version for my own shop here. So we're over at the bench, and I have my small arbor press out. I'm not using my miniature press brake, the Profiform 200. I'm not using that because we're not doing a 90-degree bend. If you use a V die and the matching lower die to do a 45, you would need to do a proper 45-degree bend, or in this case 37-degree bend. You would need a matching die and lower die, otherwise you're creating a weird shape that kind of rolls across the edge of the upper die, and it's just not a clean bend. A different way of doing it is to ditch the lower die and use a hard durometer rubber. There is a company in, I think, Switzerland who offers rubber, especially for forming and also punching purposes. Instead of having a lower die when cutting sheet metal with a punch, you can have a hard durometer rubber. I think I can demonstrate that later too. But in this case we're bending, and the idea is that the upper die with its V shape will dive into the rubber and press the material into the rubber, and the rubber will press the material up against the die and form it perfectly across the radius of the die. Let's take a tiny piece of this beryllium copper and do a test bend, just so you get the basic idea here. This gives extremely nice bends. Just like this. No weird radius tangent things, no wobbliness. It's really a nice bend. I set the depth stop kinda so I get my angle, but in reality it will not be correct. I have a test piece here that has the same geometry, means an internal corner, so I can figure out what's happening. I have a magnet here that I can stick to the side of the upper die. This is all very much a prototyping setup here. Then I can then the magnet is square to the bend line, and I can push the piece of sheet metal up against the magnet, and when I drop everything onto the rubber, the magnet will slide up and the sheet metal will slide down on the magnet, and once we hit the rubber we can do our bend. So we don't need a side stop or something like that. So let's do a first test bend here. Whoop. Okay, I see okay, this is nice. I see a minor problem here with the side, with the materials going up to the side, because it doesn't get pressed into the rubber, so we have to move all of this over. So it's the excess material is hanging off to the side of the rubber, so we don't create a weird situation here. Let's check my angle, and this is underbent. This is not enough here. But with the setup we can go back and see how we can bend it a little bit more. And we can even adjust our screw on top, the depth stop of this press a little bit. And here we go. And then we are pretty much spot on with our angle. So that's the first bend. Now we need to do a second bend from the other side, like this. And this will be a bit problematic with this configuration, because we have all this overhang back here and we cannot go down so far. One thing we could do is we could raise this block up here. We could set it up vertically. Okay, now I will cut a smaller strip of the rubber. Okay, I'm back. I bandsawed a piece off the sheet of rubber that I had. And now we can easily come back and do our second pressing here. Depends on I'm not entirely sure if this will work out nicely, but we will see. This is purely for prototyping. You would never ever do this on a production setup. A clever person would take this lower block and bolt it in place, maybe. But I don't want to. I want this to be fast and easy, which me fumbling around for 5 minutes is obviously not. Okay, let's try this again. Okay. Okay. Okay, there we go. We're getting closer. It's not ideal. It's far from ideal, but I like the quality of the bend itself. And this is really something that we often have to deal in prototyping, especially with sheet metal. When you don't want to make custom tooling or dies for a one-off. And this is really looking pretty nifty. This is, so I even get the correct dimension here for the height of this bend. It should be 4.3, and that's what I'm reading here, 4.3 and a little bit. This is making contact with something like a pogo pin in a production setup. And this is really not looking too bad. I like the quality of the bend here. So now I need to take all of my courage and do it to the real part. I really like how this came out. The angle of the bend is correct. Parallelism looks good. I have to check it on the surface plate, but this is something I can tweak with a parallel plier very easily. You just it into shape and you're good to go. Sellable product. Moment of truth. Make sure the piece of rubber in here is clean. I rearranged the camera a little bit so you see what's going on here. Double checking which way I need to bend it. And here we go, drop it down. Rubber in a little bit more. Okay, should be fine. There we go. And there we go. That's one bend. Oh yeah, I'm pleased. Let's see. Okay, that's way too little bend, so we add a little bit gronk to the brush brake. Whoop. Add a little bit more here, and from now on, oh yeah, that's pretty much spot on, maybe half a degree off, and we can tweak that with the parallel pliers or just by adding a little bit of finger pressure here. Okay, that looks good, looks correct. Now we need to do the other bend from like this, going down with the die onto the part. Okay, here we go. Aligning my part. I have a pencil mark on here where to put the die. Let's see what we got. Okay, that's. I shouldn't have adjusted the depth stop of the press. Got it way worse. So let's repress this. Nice thing, once you get a bend in there, it's kind of self-aligning on the upper die. Okay, that looks better. That looks way better. Okay, here we go. I sheared the end to length. I just took the height gauge, scribed the line, sheared it to length, cleaned up all the edges, and part is done. Off for gold plating and ready for delivery. That's one neat part. Hardest feature is probably the 0.25 by 5 degree chamfer all around the perimeter of the part. But wait, I forgot the pictures of the gold-plated parts. Here they are. After copper flash, nickel plating 5 micron, 1 micron gold plating. And the gold plating shows every minor surface imperfection in the part perfectly fine to the eye. So that's great. Thank you all for watching, and I'll be back.